Example 1 says this. A mass, little m, let's make it a little rocket, is moved from the surface of a planet to a distance r from the planet's center. Which of the following is true about the work done? First thing, looking at the picture, is this in a stable orbit? No. If it was in a stable orbit, they would have oriented the rocket ship in that direct, like they would have had it going around in a circle. It looks like, Zach, they've just fired the rockets to go straight up, and when they turn the rockets off, they're going to come straight down. You okay with that? Okay. What does this want me to find, Zach? Looking for a word that starts with letter W? So my first thought was, maybe I can go, like, don't write this down. Maybe I can say it's force times distance. Why doesn't that work in this case? Force of gravity is changing, so all of you can cross out A. How am I going to find work? I guess I'm going to use the work energy theorem. And the work energy theorem says that the work is the change in potential plus the change in kinetic. Looking at this, it's moved from the surface of a planet. I think they use that phrase deliberately. Paige, I think they're trying to say you started and ended at rest. I think they're trying to imply that. Paige, what's change in anything? You know this. You knew this. I know. You're waking up. That's what happens when you show up late. Yeah, I said it. So this is going to be potential energy final minus potential energy initial. Don't write this down. So is that this? Why can't I do that one? Little g is changing. Okay, so we have to go cosmic. So it's going to be final, negative, big G, big M, little m over R final minus negative, big G, big M, little m over our initial. Does the little m cancel here? Well, there's a little m there. There's a little m there. Is there a little m in work? No, okay. Okay, it shouldn't cancel. It should take more rocket fuel to put a bigger rocket up. It should be more work. Okay. What's the correct answer? B, C, D, or E? D. Well, Mr. Dewick, there's a big G in both, a big M in both, a little m in both. Couldn't you factor it out? You could. I've seen some textbooks, don't write this down, do it this way. They factored out the big G, the big M, the little m, and then what you have left behind is negative 1 over R final plus 1 over R initial. I've never found that significantly less typing than just typing the first one, hitting equals, writing it down to 5 sig figs, backspacing and editing, and just changing the numbers to get the second term. I played around with it. No. And none of those showed up there. It says explain your answer using principles of physics. I think we did. We just derived it from the work equation. Let's keep going. Let's talk about escape velocity. I like escape velocity. It's going to be on your test. What's escape velocity? Here's our physics definition. It means theoretically to travel an infinite distance from the planet, so there's no more gravity. If Aiden was here, he would say infinity. Well, you know what? In reality, it means to get so far away from the planet that the gravity from that planet is negligible. You can ignore it. To barely escape means to escape from a planet with no kinetic energy left at the end. So you end up at rest and at infinite distance. So, Sarah, what we mean by escape velocity, you fire your rocket in a mighty burst, and then you shut the rocket off and you start to coast. As you coast, gravity will cause you to slow down, slow down, slow down. But you've got just the right speed so that even though you're slowing down, you're getting further and further and further away. In fact, you've done it so perfectly that right when you get out to the edge of the universe, that's also right when you come to a stop. Mwah. That's escape velocity. So escape velocity asks, how much kinetic energy is required to bring potential energy to zero? Say, what? escape velocity is a conservation of energy question. It should be called escape speed because it is a scalar, but in the literature they always call it escape velocity, so I'll use that term, even though, Braden, you can imagine it's fingernails on the blackboard of my heart because it's a scalar, not a vector. Okay. Let's derive an equation for escape velocity. This is not how much work, and the reason I know that is I didn't ask you how much work. We're finding a speed. Is there a change in height as we leave the planet? Yeah. Is there going to be a change in speed? Yeah. Is there a yucky, curvy, decreasing force? That's also a good job for conservation of energy. So we're going to write KE initial plus PE initial equals KE final plus PE final. I wrote on the next page we can solve for escape velocity using conservation of energy, but I'm doing it on this page here as a start. Are any of these zero? Sarah, do you remember I said we want to plan this so well that when we get to the edge of the universe, we come to a stop? So you know what's zero? KE final. Oh, and you know where we're ending up? Out at the edge of the universe, at infinity. What else is zero then? Yeah, this is a little bit strange. I have this on the next page. KE initial plus PE initial equals zero. What? Well, don't panic. What's our equation for kinetic energy? That hasn't changed. That's still what it was earlier this year. Something, something, something squared. Okay, that hasn't changed. Let's draw a little arrow. This is going to be a half mv, and instead of initial, I'm going to put, that's my escape speed. That's how fast you need to be going. Plus, for potential energy, can I use mgh? Or are we going cosmic? We're going cosmic, so it's going to be negative big G, big M, little m over R initial. That equals zero. You know what I would do next? I think, Zach, I would plus this negative onto the side of the zero. That gives me two positive expressions. So I would plus this over to there. That's going to give me a half little m escape speed squared equals positive big G, big M, little m over R initial. R initial is wherever you're starting in relation to the planet. Oh! Is the escape velocity for a small probe satellite the same as the escape velocity for a giant mega ship? Turns out it is. Little m cancels. I want to get the v by itself. How? I'm going to times by 2 instead to make it, I'm going to go times by 2, and then square root. And yeah, this gives me my escape speed, although they call it velocity, equation. Square root of 2 big G, big M over R. I'll put an initial there where you're starting. Huh. Does anybody remember the orbital speed equation? I wrote it earlier during our thought puzzle. That was, don't write this down. It looks like getting an orbit is really tough. To leave the planet, you only need to multiply by an extra root 2. What is the square root of 2 on your calculator? Yeah, you only need to be going 1.41 times faster. It's way tougher to get off the planet. Almost all of our efforts, all of our rocket, all of our energy, it's designed just to get us off the planet and into orbit. Once you're there, it's way easier to keep going, but getting there is the tough part. So, example 2 says, find the escape velocity for the Earth and for the Moon. Okay. I don't think I gave you the escape speed equation on your formula sheet, did I? Because it comes out of conservation of energy, G, and you will need to derive it. Now, I have some kids that just memorize it, and you can if you want to. I'm going to rederive it for part A. I'm going to say to myself, okay, you want me to find the escape velocity for the Earth? This is a job for conservation of energy, G. And we have this weird situation, Sarah, where my final is 0 and my final is 0. And I end up with a half mv initial squared plus negative big G big M little m over R initial. That equals 0. Then I choose to plus that negative term over, makes it way prettier. I get a half little m v initial squared equals big G big M little m over R initial. Ha ha! I smile, Garrett, and say, little m cancels, always a bonus. And I have just rederived the escape speed equation, times by 2 square root. So let's plug in the numbers for the Earth. It's going to be the square root of 2, 6.67 times 10 to the negative 11, mass of the Earth. And we're starting out on the surface of the Earth, so 6.38 times 10 to the 6. We're ignoring air resistance, but basically, if you got a little distance into orbit, out into space, out of the atmosphere, this is the speed that you would need to then hit if you wanted to keep going and get to the edge of the universe and visit other stars. What do you get? This is one that's worth practicing typing in because we're getting some pretty heavy-duty expressions. What'd you get? No. I think you forgot the square root. I think you forgot a 2. Got to be impressed that I can tell what your silly mistakes are here. I know I've kind of almost memorized it. I know it's almost exactly 11,111. It's almost 5 ones. It's not quite, but if you're looking for that's my dumb way because I'm a nerd and I know this. It's 11,000 something. What is it? 11,200 basically. Do we have the technology to do that? Yes. The Apollo rockets did that. They achieved escape velocity. That's how they got to the moon. They went fast enough, then they coasted until they got into the moon's gravitational pull, and then the moon caused them to accelerate. What about the moon's escape velocity? You got those of you that made mistakes, you got it okay? By the way, you're 10 to the 8th, that was like 1/3 of the speed of light. No. Right? Because 3 times 10 to the 8th is the speed of light. 1 times 10 to the 8th, no. You should have caught that. Let's do the moon then. I'm not going to rederive it, but I am going to need the numbers for the moon. These ones I haven't memorized. I mean, I know big G. I think I said yesterday I'm going to start writing capital G instead of writing out the 6.67 times 10 to the negative 11. And if you want to start doing that, I'm okay with that. Mass of the moon, I think it starts with a 7, but I can't remember anything else beyond that. It's on your sheet somewhere. Taryn. 7.35 times 10 to the, you said 22?
Yes.
Okay. And we're starting from the surface of the moon, so what's the radius of the moon?
1.74 times 10 to the 6.
Okay. What do you get? This is why NASA wants to build moon bases. Launching from the moon, way easier. I think is it in the 3000s, I think? I might be totally wrong. That one I haven't memorized. 2000.
2,374.
So 237? Way less. And remember, when we're talking about energy and fuel, there's a squared as you're getting bigger. Way less rocket fuel to get to, say, Mars from the moon than from the Earth. Way, way less. The problem would be, does that work? Yeah. Can we manufacture rocket fuel on the moon? What are the ingredients for rocket fuel? Yeah, we think we have found water on the moon. If we find substantial water on the moon, H and O. We think. We're pretty sure. By lots of it, what you really mean is the several craters that we've checked have lots of it, but that could be a fluke. Maybe just towards the only 3 or 4 craters that happen to have water. We need to do more exploration. But yeah, it's looking good. It's looking good. There's really no such thing as the dark side of the sun hits that too, right? Just saying. Okay. Note, this means that meteoroids and asteroids will impact a planet with at least escape velocity. And the reason is they'll gain all that kinetic energy coming back. Oh, and if they had any of their own kinetic energy to begin with, they're hitting with at least kinetic energy, with at least escape velocity. This is why asteroid impacts do damage. They're moving. So for the Earth, they're going faster than 11 kilometers per second. Oh, also, you can reach infinity and still be moving. That work equation would look like this. K E initial plus P E initial equals K E final. There would be a little leftover energy out at infinity, but your potential energy out at infinity would still be 0 because that's where we've defined 0. And hopefully you're also now starting to see why actually we thought about this. It was clever of us to define 0 out at infinity, not on the surface of the Earth. Spaceship is 8.5 times 10 to the 9th meters from the center of a black hole. The black hole has a mass 50 times that of the sun. What's the gravitational field strength at that location? I like this question. I like this question. I like this question. I am going to ask you to find the gravitational field strength. And inevitably, some kids throw away silly marks, especially if they haven't consistently been doing the homework. What do I want you to find, Arsh? Say it again. You're right. Every year I have some kids who say this, gravitational field. Hey, that starts with an F. Don't write this down. And they go, okay. You haven't found gravitational field. You found gravitational force. And I have to give you a 0. Even if you did it right. No, it wasn't what I asked for. So here's the question. What's our symbol for gravitational field? Which one? Little g. And the formula that I've given you on your formula sheet says it's that divided by that. But we're cosmic. Big G, big M, little m over r squared divided by little m. Hey, little m cancels. It's big G, big M over r squared. That's gravitational field strength. What is it near this black hole? What is it on the surface of the Earth? You all know this. 9.8 newtons per kilogram, which is why we accelerate at 9.8 meters per second squared. What about near this black hole? Let's find out. G, 50 times the mass of the sun. What's the mass of the sun? I don't know. I think it's 1.98, but I can't remember the time. Times 10 to the 30? Divided by r. Oh, they told me. 8.5 times 10 to the 9th. Don't forget the squared. What's the gravitational field strength there? Oh, do you think it's going to be bigger than 9.8? Probably. Doesn't have to be. We could be so far away from the black hole that actually G could be small. Now, I'd put us reasonably close. What'd you get? Oh, for Pete's sakes, people, we need to practice typing this stuff. Nicholas, what'd you get? 91.4? So roughly 9 times bigger than Earth's gravitational field. Units. I would take meters per second squared, and I'll give you full credit. Usually for gravitational field, because it's a force divided by a mass, I'll usually write newtons per kilogram, because that's the units that kind of popped out of my approach. But that also is meters per second squared in disguise, and so I would accept either. Is that right? Yeah? Amrit, we're good? Okay. Amrit, what's B want me to find?
Speed.
What kind of a speed? Psst, psst, psst. What kind of speed? Oh, escape speed, escape velocity. Okay, you may have memorized it, but let's rederive it just in case we blank out on a test. How did we find escape velocity? Conservation of energy. So we started out by going kinetic initial plus potential initial, but it was kind of strange. It equaled 0 because we wanted to have no energy left over at the end. No kinetic. We wanted to exactly come to a stop out there. And, if you're all the way out in infinity, you have no potential energy. Why? Because you won't fall if we let you go. We ended up with a half mv squared plus negative big G big M little m over R. That equals 0. I guess these are both technically initial and initial, but because they're the only ones left, I got sloppy and didn't bother putting those in. What did I do next? Get rid of that negative, and I ended up with a half mv squared equals positive big G big M little m over R. Then it was, the little m's cancel. That's good because they didn't give me the mass of the spaceship. I times by 2 square root. So it's going to be the square root of big G 50 times 1.98 times 10 to the 30th all over 8.5 times 10 to the 9th, no squared. You know what? You might be able to backspace and edit the previous question. I think if you just delete the squared, hit equal, square root answer button. That's probably what I would try and do. It's going to be bigger than Earth's, so it's going to be larger than 11,200. How do I know? Stronger gravitational field right there. Amrit, what'd you get? Okay. And yeah, for this rest of this unit, I can't encourage you enough. Type everything in during the lessons. This is the practice. It's a lot of typing. Okay, I gave you a head start. Let's see if I can race you. Square root bracket 6.67 times 10 to the negative 11 times 50 times 1.98 10 to the 30 divided by 8.5 times 10 to the 9th. What'd you get? Did you get 8813? Is that right? I forgot the 2, Mr. Dewick. Oh, wow. I made a mistake. I'm totally wrong. It's going to be even larger than that. Is it 1, 2, 4, 6? Wow. I'm going to write this in scientific notation as 1.25 times 10 to the 6th. Meters per second. Can't believe I forgot the 2. Thank you, Mud. That was sloppy of me. 2g square root. Now that we know how to do escape velocity, we can start to talk and analyze black holes a little bit. George, what does C want me to find? The event horizon. What's the event horizon? That's the spot where the black hole starts becoming a black hole. If you're further away from that, then escape velocity is less than the speed of light. If you're closer, escape velocity is more than the speed of light. Can anything go faster than the speed of light? In other words, once you're past there, you ain't coming out. This is the event horizon. This is the spot where there's no coming back. Okay? We're going to start out with the escape velocity equation. V escape equals the square root of, Mud, you're right, don't forget the 2, big G, big M over R. How far away? What's this wanting me to find in my equation, do you think? Okay, we're going to get R by itself, but here's what else. We're going to let V equal the speed of light. That's where it happens. We're going to say, where does the escape velocity become the speed of light? That's where the event horizon begins. Okay. First, I'm going to get the R by itself. The R is inside a square root. How would I get rid of a square root? I'm actually going to end up squaring both sides. That's going to give me V squared equals 2 big G big M over R. Where is the R right now? On the... Bleh. Oh, is this 1 fraction equals 1 fraction? Well, then, my friends, stuff can move diagonally. I can move the R there. I can move the V squared there. I'll have R equals 2 big G 50 times 1.98 times 10 to the 24th divided by 30th. Thank you. This is what happens when I go from memory. And V is going to be the speed of light, which was 3 times 10 to the 8th. Don't forget the square. Oh, I like this question, I like this question, I like this question. And to me, it's kind of interesting. Where is the event horizon of this particular black hole? You know what? I'm going to backspace, delete the square root, but now I've got 2 times G times that. I just need to divide by 3 times 10 to the 8th squared. I didn't need to retype all that. Did y'all get 146,740 meters? If I wanted to make it kilometers, 147 kilometers from the center of this black hole, that's where the event horizon starts. Or, here's the other way to think about it, Braden. Let's suppose that you are in charge of the universe and you want to build a black hole. If you have 50 times the mass of the sun, you would have to compress that mass, continue to compress that mass, and it would turn into a black hole once you had compressed it so small that its radius was 146.7 kilometers. Well played. It's called the Schwarzschild radius. Yes. 146,000, what was it, 740? Yeah, that's called the Schwarzschild radius. Example 4. We're going to do a lesson on black holes next class, but let's try and look at, well, here's a good example. This, I think, is the longest question that I can ask you. I warned you about it. Here it is. How long is it? Well, let's find out. Garrett, what are they asking me to find? Keep reading. Stable what? Stable what? Okay, notice the picture. This is different from just lifting it into outer space. If we were just lifting it into outer space, we could say it's just the change in potential energy. But we're putting it in a stable orbit, so it's also going to be the change in kinetic energy. Write that down. I'm not going to do both of these at once. I'm going to do them separately. What would you like to find first? Change in potential plus or change in kinetic? Okay. Paige, what's change in anything? Yeah. So I'm going to go, the change in potential is going to be negative big G big M little m over our final minus negative big G big M little m over our initial. I have a minus minus, which is a plus. That'll be on my next line. Okay. The change in potential is going to be negative big G, mass of the Earth, 5.98 times 10 to the 24th. Mass of the rocket, 12,500. All over our final. That 25,500 kilometers, first of all, it's kilometers, so I'm going to multiply it by 1,000. I'll do that in this. 1,000. Yes? Is it a radius or an altitude? Read the question. Do I need to add the radius of the Earth to that, or have they already done that for me? They've already done that. So I'm just going to write down here 25,500 times 1,000. Then there's a minus minus. What's that? And then it's going to be the same thing times the same thing times the same thing all over. But I think my initial radius is, it looks like I started on the Earth. 6.38 times 10 to the 6th. Yeah, now I'm going to get out my calculator. I'm going to do the first expression to like 5 sig figs. I'll backspace and edit. I'll do the second expression to like 5 sig figs. Then I'll add them up. So negative 6.67 times 10 to the negative 11 times 5.98 times divided by bracket. And I got a typo. Let's go fix that, Mr. Dewick. Negative big G, big M, little m over R. And I think for the first one, I get negative 1.9943 times 10 to the negative 11. We agree? And you'll notice this is heavy-duty typing enough that I'm uncertain. Normally when I'm asking you, I know what the answer is. Here, I might have made a mistake. This is some heavy-duty typing. So be really, really meticulous and careful. What did I say? Negative 1.99433. Negative 1.99433 times 10 to the 11th. I don't know if you've noticed, but typically when we're doing potential energies around Earth in orbit, it's in the 10 to the 10th or 10 to the 11th range. Here, we're pretty far out, 25,000 kilometers. That's a very far orbit. Plus, I'm going to backspace and edit. I'm going to delete the negative, and I'm going to change the radius in the bottom to 6.38 times 10 to the 6th. And I get positive 7.8148. 7.8148 times 10 to the 11th. Notice, Braden, I will get a positive answer when I add these two together. Of course I will. It will take rocket fuel to get it up there. So even though they started out negative, that minus there gave me a positive that was bigger than the final negative. So it all works out as long as you're careful with your signs. Now I'm going to combine these. So it's going to be that number plus negative 1.99433, scientific notation 11. And I find the change in potential energy is 5.8204 times 10 to the 11th. Joules. Did I read that right? 5.204. Yeah, it looks good. Whew. My fingers are smoking. I've been typing so much. Red hot. Garrett, are we done? In fact, what I usually do is, oh, geez, that's terrible. I often put a box around this so I can find it later because I got more writings to do's. I need to find out the change in kinetic energy. So I'll often just draw a little line. Okay. Change in kinetic energy. That's going to be a half mv final squared minus a half mv initial squared. Are any of these zero? Where did we decide that we're always launching our rockets from? North Pole, right? You can either say Santa Claus has a rocketry program or Superman's Fortress of Solitude, which everyone knows is in the North Pole. Wow. So if we launch from the North Pole, we can ignore Earth's rotation. Oh, and I think I told you in real life, we deliberately don't. We launch as close to the equator as we can. This is why Elon Musk is trying to learn to launch from ships. It's tricky because ships move on the ocean and you don't want your rocket platform moving, so they need to figure out a way to do that, but ideally that would be a good way to do it. Do I know the LM? Do I know the speed? No. In fact, you know what speed this is? This here is actually the orb. I guess I'm going to have to calculate that too. That's why this is the longest question I can give you with the least amount of information and the most figure it out yourself. So, okay, he looked at his formula sheet and he wasn't sure, so I fibbed. We're going to have to go like this. How are we going to find V orb? V what? Are we in orbit? A stable orbit? And the question said so? Well, then gravity is what's pulling me in a circle. I can say that. I can say big G, big M, little m over r squared equals m. Which version of A should I use here? Which version of circular acceleration should I use here? The one with the T in it or the one with the V in it? Yeah, I want to find orbital speed, not period. Hey, little m cancels. Does an R cancel here? Oh, R cancels. Oh, how would I get the V by itself? I remember this. V orb is the square root of big G, big M over R. Wait. Look up. What do I have right here? Don't write this down yet. Garrett, look up. What do I have on the V right here? Why don't I just replace the V squared right here with a big G, big M over R? Because it's squared. Why not? So I guess another way to find the kinetic energy in orbit, it's a half little m, big G, big M over R. Now, why is that nice? If I backspace a little bit, now if you can go back 2 lines on your calculator, I can't help noticing I have big G, a big M, and a little m already typed. I think I just need to multiply this by a 0.5 and divide by R final. Less typing. Insert 0.5 times. And R, I'm ending up in orbit, so not the radius of the Earth. It'll be 25,500 times 1,000. Close off the bracket. If you can't go back more than one line, oh, you poor schmucks, you'll have to type this yourself. I get the kinetic energy is 9.7761 times 10 to the 10th. Are we done? What did this question want me to find? How do I find the work? More specific here. I think I'm going to add the two boxes. Oh. We've come a long way, Zach, from Physics 11, where it was, oh, just write down what they gave you, plug and chug, right? The work is going to be the change of potential 5.8204 times 10 to the 11th plus 9.7761 times 10 to the 10th. I can just go plus answer button, thankfully. And no pun intended, this question is a lot of work. And we also get a lot of work. 6.80 if I go to 3 sig figs times 10 to the 11th. And that's energy joules. So if you knew how many joules of energy you get per liter of rocket fuel, now you know how much rocket fuel. It's more complicated than that because we're ignoring air resistance. Also, m isn't constant, as little m isn't constant. Braden, as the rocket burns fuel, little m gets lighter and lighter. And so this really, to do it properly, you need to use a calculus-based approach, but this is our starting point. Okay. I don't like this question. I don't like this question. I don't like this. Taryn, could we handle it? Yes. I am going to ask you, I guarantee you on your test, how much work to put something in orbit, but I'll give you the orbital speed. I won't make you calculate it. There will be a separate question where I ask you to find orbital speed, orbital period, or orbital radius, but I won't combine them into this one. So I will say how much work to put something in orbit, but I'll tell you, and with an orbital speed of 3,217 meters per second or something like that. We're going to finish with this and then press pause. Example 5, you can take it or leave it. This is a handy error check. You can absolutely survive without this, but it's kind of a neat pattern. Here's what it says. Use the expression for orbit speed, big G, big M over R squared. Actually, I'm going to use the expression for orbit speed squared, which is just big G, big M over R. Prove that in a circular orbit, the kinetic energy is half the magnitude of the potential energy. Say, what? Mud, can you read me the first half of the sentence? You know what? Read to me the first 2 words. Good. A half mv squared is equals the magnitude. What do they mean by the magnitude? Ignore the negative of potential. What's the potential energy equation if we ignore the negative? Are those two the same? Let's find out. Replace this expression for V orb right there. I'll get a half little m big G big M over R. Big G, big M, little m over R. Big G, big M, little m over R. Half of that. Is that correct? Okay, so what does that mean? Let's suppose you're doing a question and you're in orbit and you know that the magnitude of the potential energy was 10 million joules. The kinetic energy is 5 million joules. I've never used that to find the kinetic energy, but if I was solving the kinetic energy and I got 5 million, I would glance at the potential. Ha! It is half. I must have done this right. That's what I use it for. Mud, what's the second thing they want me to show? The total orbit energy. What would the, you know what? I'm going to use TE as my abbrev for total energy. I guess that would be potential plus kinetic. Add them up. Well, potential is negative big G, big M, little m, all over R. And we just showed that kinetic was 1/2 big G, big M, little m over R. Those are like terms. That's really -1 plus 1/2. What is -1 plus 1/2? Big G, big M, little m over R. Can you read me the sentence again, Mud? Part 2. What do you want me to prove? Right there is, keep reading, is, keep reading, half the potential. Yes, it is. Again, I can survive without that just fine. I use that sometime as a built-in error check. Oh, I noticed that when I was solving it. Good, I probably did this right. Mud, read to me the third sentence. Stop. This. Keep reading. Are they identical, but one's positive, one's negative? Yes. Trivial. Duh. So some nice patterns, but it's not like you need to memorize this to get a question right on the test. We're going to continue this, but for now, you have homework from last day. I've really finished the unit. All I'm going to be doing is showing you more ways this fits together, and I'll talk a little bit more about black holes. But for now, you can try number 1, where it says write a work energy equation, cross out the word work. It's just write an energy equation. Number 3 is good. I skipped number 2. Five is good. I skipped number 4. 7 is good. I skipped number 6. 8, this is the long question where you have to figure out everything. The change in potential, the change in kinetic. They didn't give me the orbital speed. By the way, when it says RTZA relative to 0 at infinity, that's saying make sure you use the cosmic potential energy equation. Don't use MGH. Can't do that. Yeah. Let's go. 10 and 11, these are both pretty tough. Skip 12, 13, and 14 because we did all those in the notes. '16 is good. Skip 17, 18 is good. 19 and 20. These are not due Monday. You're not going to get much more homework on Monday. Because I've thrown a lot at you. I'll finish the lesson off on Monday, but this is also, you'll get time to work on this on Monday.